It's my distinct pleasure to introduce the last speaker of this workshop, Jean-Philippe Ronin, and he will speak about trend series and discrete dynamical systems.
Thank you, Selma. Okay, hi everybody. Thank you to the organizers for inviting me to give a talk in this nice workshop so far. And okay, thank you also to the organizers of the semester for letting me stay here during the almost entire semester now. Okay, so I am going to, in my abstract, I announced a kind of survey on the topics which are on the screen now. Well, survey is a big word. I mean, I'm going simply to pick 2 or 3 points in this story which I find amusing and which may be of some interest for you. I think it will be enough for a talk. So for those of you who are not so familiar with the notions involved here, let me recall a few facts. The beginning of this history is the study of discrete complex dynamical system, meaning you consider a holomorphic map F from an open set of the complex plane to itself with a fixed point, 0, let's say, and you want to understand the behavior of the orbits of this map, meaning that if you take a point, you apply F repeatedly to the point and see how the set of iterated of F applied to the points behave. Obviously, you agree that if you try to do this computation from scratch, starting from the Taylor expansion of F, immediately the computation will be intractable. So usually what people do, they try to simplify the expression of F via an appropriate change of coordinates. So what we're going to do, what do people do in this problem? They try to classify F modulo a group, an appropriate group of changes of coordinates, and leading to a hopefully simple normal form, which is a particular conjugate of F via an element phi of the group, and we expect the normal form to be simple. That's the point. So as you can guess, it's a matter of balance here, because if you work with a big group of changes of variable, you could expect a simple normal form. But at the same time, if your group is too big, it would mean that your classification will be coarse. So you have to balance between these two obligations. As we say in French, you cannot have at the same time the money on the butter and the creamer's daughter. That being said, so what kind of groups are canonical in these questions? So the first group is the group, when I say group, I mean group for the composition of applications. So the first group is the group of analytic germs at the origin, tangent to the identity, meaning that their expansion are Z plus higher order 10. And the other group, which is a bigger group, is the group of formal series, tangent to the identity, with the same kind of expansion, but formal. We do not impose to the series to converge anywhere. So according to the people who have studied that long ago, it seems that there is a classification of the fixed points which depends mainly of one number, which is called the multiplier of F, which is nothing but the derivative of F at the origin. So let's see, I'm going to show you a few items of the classification they have obtained by showing you simply a few results, not the complete results, but some of them, which may be of some importance to me afterwards. So the first result is called the hyperbolic case, and which is, this result has been obtained by a French mathematician, Koenigs, in 1884. So what does it say? It says that if the multiplier, lambda is the multiplier, that is the derivative of F at 0, if the modulus of this complex number is strictly between 0 and 1, then there exists analytic linearization of F, that is analytic change of coordinates which conjugate f to its linear part, which is simply lambda times z. So this is the kind of best result you can expect in this kind of problem. Second result obtained a bit later. Sorry, a comment about that, about the proof of Koenig's. Define the operator P of Pf, which acts by the composition on the left, of f on the left, as it is written here. Define also MA, which is simply the multiplication by the complex number A. It's straightforward that the conjugation equation between f and its linear part can be rewritten in the following way as a fixed point equation, namely m sub lambda minus 1, that is the multiplication by lambda, the inverse of lambda, composed with the precomposition operator Pf applied to phi equals phi. So the conjugated map appears as a solution of a fixed point problem, holomorphic fixed point problem. So it suggests to solve it via a Picard sequence, as people classically do it, and it works. This is how Koenig proceeded. So it is classically called in literature the Koenig sequence, that is the iterate of f iterated n times divided by lambda to the n. So he proved the convergence of this sequence of holomorphic functions in a small neighborhood of the fixed point. And so the limit of this sequence will be your linearizing map near the fixed point. The second result, the first result is hyperbolic. The second result is strongly hyperbolic, obtained by Butcher. In that case, the multiplier is 0, and f, so meaning that f of z, the expansion of f, started with a power of the variable bigger than or equal than 2. In that case, you can conjugate analytically to simply z to the p. So it's also quite a nice result. So you have a normal form, which is as simple as possible. Third and final result of this history of holomorphic classification, which is the most difficult one. So it has been solved by two French mathematicians, Lowe and Fatou. And here, typically, the two groups of conjugations will play a role. The first group will be the group of formal change of coordinates. Namely, what is the parabolic case? I forgot to say, the case where lambda is exactly equal to 1. The multiplier, remember that it is f prime at 0, is exactly equal to 1, meaning that f is, as we say, tangent to the identity. In that case, after a change of variable, you can assume that the first coefficient after z is exactly equal to 1, that it is a little trick, kind of pre-preparation of the result. And then f can be formally conjugated to this normal form here, which is a polynomial, which is the sum of 3 terms here. So you have here a quite simple normal form, which is a polynomial of with a few terms. Am I clear? So the natural question when you have such a formal result is, do we have the same result on the analytic side? So is f holomorphically conjugated to such a polynomial? And the answer in that case is no. But we have still a beautiful description of the dynamic of f in the neighborhood of its fixed point, which can be symbolized by the following picture. That one. It's called usually the flower dynamics of the f. So what does this picture present? It says that in the neighborhood of the fixed point, you can cover a punctured neighborhood of the fixed point by simply connected open sets, which are in turn attracting or repelling. So in my picture, the bold domains here are attracting, and the not bold domain, the thin domains, are repelling. So what does mean attracting or repelling? Attracting means that once the orbit of a point intersects an attracting domain, it is trapped in here, and the orbit will be attracted by the origin, tangent to the bisecting direction of the domain. Usually these domains are called petal, and so you have a complete description of the dynamic of F near the fixed point here. As you can see, it's more complicated than the two previous cases. Am I clear? And you have, moreover, for the problem of normalization of F, here is the results that have been proved by Low and Fatou. Let's consider an attracting petal on this picture. So for each attracting petal P, there exists a conformal embedding alpha from the petal to its image, which is an open set of the complex plane, such that alpha P first contains the right half plane of the complex plane, and second, alpha satisfies the Abel equation for F, meaning that alpha conjugates F with a translation by 1. Namely, you have this equation for every Z in the petal, alpha of F of Z is equal to 1 plus alpha of Z. So you have a normalization petal by petal, an analytic normalization petal by petal, but you do not have a germ at the origin of the picture, which satisfies this conjugation property. This works only petal by petal. Okay, this is basically what we can say on the complex situation in one variable. But after that, people also consider real maps of the interval. For what reason people are interested in real maps of the interval? Geometers usually work with, some of them work with foliations of codimension 1, meaning that the leaves of the foliations are submanifold of codimension 1 of an ambient manifold. And in that case, you can say that a foliation of codimension 1 can be treated as a dynamical system, because you have an algebraical object associated with the foliation, which is usually called the groupoid of transverse holonomy, which acts on a transversal that you can draw, transversal to the foliation, and you see how the foliation acts on this transversal. So this action is actually in dimension 1. So again, we want to study maps on the line because of that. So what are the results in that case? So now we are not holomorphic anymore, but we are see something. We have some regularity of the map. One of the most useful results is due to Sternberg. Again, we work for real map in the hyperbolic case. So let me remind you what hyperbolic means. It means that F now is of class CR. You again have a fixed point 0, and you assume that the regularity of F is high enough. That is, F is of class CR with R bigger or equal than 2. That's an important hypothesis here. Okay. And hyperbolic means that the multiplier, remember that it is the derivative of F at 0, is not 0 or 1. In that case, there exists a change of coordinate phi of the same class of regularity, CR, for which the derivative at 0 is equal to 1, such that when you conjugate by phi, you linearize the initial map F. So you have exactly the same result that we had thanks to the result of Koenig in the holomorphic situation. So you see that you need here some regularity high enough. You need C2 in this result. So obviously the question is, can we go a bit further? Can we weaken the hypothesis a little bit? Well, yes. If you consider, I didn't write it on the screen, but if you consider a map F, which is of class C1 plus epsilon, what does it mean? it means that f first is C1 and that the derivative satisfies a Holder condition. In that case, Sternberg works as well. So what about exactly C1? Well, in that case, it fails. And Sternberg himself gave a counterexample, which is the following one. You consider a map, so here it is on the positive neighborhood of the origin, extended by 0 at 0, and f is exactly equal to lambda x multiplied by 1 minus 1 over log x. In that case, so this, it's easy to see that f is of class C1. It is not C1 plus epsilon. And in that case, f is not C1 conjugated to its linear part lambda x. So it's a negative result here. So it may happen if you are not regular enough. Actually, it's not even Lipschitz conjugated. So it is one of the most negative results we have in this setting. And more recently, we discovered an amusing result proved in 2002, which says the following thing. So always playing with what can we do between C1 and C2? So can we still expect some positive linearization result? So what does say this statement here? So consider f acting on a small right neighborhood of the origin, again with 0 as a fixed point. You call, as usual, lambda the multiplier of f, as you assume, as usual, that lambda is strictly between 0 and 1. And you add an extra hypothesis, which is going to be between C1 and C2. So let's analyze this hypothesis. If f of x is equal to its linear part, lambda x, plus a big O of the following quotient, x divided by y, where y is a shortcut for log of x, multiplied by log of y, multiplied by log of y, and so on and so on. Multiply at the end by log p minus 1 of y, and multiply also by log p of y raised to a power 1 plus epsilon, where obviously epsilon here is a strictly positive number. So here, under this hypothesis, you have the linearization property. So you have a version of Sternberg's theorem here. So you see that this map here has an asymptotic behavior, which has a bit, how can I say that, a transserial flavor because of this accumulation of logarithms here. So here I precise a bit the notation. Epsilon is positive, and for some p equal integer, of course, if p equals 0, it means that the quotient is x divided by log of x raised to the power 1 plus epsilon. So the important thing is the power 1 plus epsilon here, which makes the things work. And the proof uses the classical theory of so-called Bertrand series, if it means something for you. It's a classical exercise in which you can study if a Bertrand series converges or not. And this is one of the tools used by these guys. Okay, so as you can guess here, we are slowly going to what I'm going to call transserial germs, whatever that exactly means. Okay, so here is the conclusion of this example. The Koenig sequence converges to a linearizing map. Okay, so what is a good source of transserial maps, whatever that means? It is that picture. Do I really have to comment that picture? Is there anybody in this room who have no idea of what that picture means? We have 6 hours plus courses. So very basically, so you have here a monodromic polycycle of a real analytic vector field. You have a trajectories, which is attracted by the polycycle, and a green transversal to one side of the polycycle. And this is typically an example where codimension 1 leads you to a dynamic analysis on the transverse direction. Yeah, that is, to understanding the behavior of the leaves of the foliation. You see how it acts on the transversal. So here we are introducing the first written map of Poincaré, which studies how you can go from one point of intersection of the transversal and the trajectory to another point of the same transversal. So this is a beautiful source of what I could call a transserial germs. Again, whatever that exactly means. Well, we know, for example, that in the non-degenerate case, the asymptotic expansion of such a germ is a Dulac series. That is a series involving powers of the variable and polynomial of the logarithm of the variables, typically. Okay, so I can summarize in one sentence all the rest of my talk. Isn't it good news for you? Yeah, you can do a picture, whatever you like. Yeah. So what is this sentence? I mean, if you remember the word I have introduced before, hyperbolic case, strongly hyperbolic case, and parabolic case, well, try to keep this classification in mind. We would like to do similar things as we have seen before in the holomorphic case or the real case for C2, C1 plus epsilon, and something like that. We would like to obtain similar results for transserial germs. That would be fantastic. But before doing that, we have to prove the result totally on the formal side, that is for transseries. This is not done yet. So with a bunch of colleagues I'm going to quote now, we proved similar results, and my sentence is the following. Each of the statements I have showed on the first slide, hyperbolic, linearization hyperbolic, strongly hyperbolic, and the normal form in the parabolic case, each of these statements has an analog on the side of logarithmic transeries. So briefly and roughly, this is the kind of results I'm going to present now. So if some of you want to leave, you basically know the heart of the talk. Alors, be careful of the word analog. Analog doesn't mean verbatim. Analog means basically analog. Okay, so let's go further. So I am not going to show you a long and tedious list of results, which would be boring and which you will forget immediately after the talk. I prefer to show you 2 or 3 things, tricks that we use during the proofs of these results, which might be more amusing for you, let's say. Okay, first result, we introduced the class L1, meaning logarithmic transeries of logarithmic depth 1. That is, we do not allow iterated logarithm in the monomials of the transeries. And here we had a result with Pavao Mardejic, Maya Resman, and Vesna Zupanovic. I hope you enjoy, as I do, the beautiful music of these Croatian names, because it's not over. A few years ago, because of the history I just showed you, the transeries we consider for us the variable x, unlike other presentations of transeries, the variable x for us is infinitesimal and not infinite. We always think that we're close to 0. This is why we introduce L1, which is not the logarithm of x, but -1 over log of x, in order that the logarithm is also positive and infinitesimal. So in that case, I am going to study a parabolic logarithmic transeries. So what is it in our setting? So it starts with x. Parabolic means tangent to the identity. Then you add terms made of powers of x multiplied by integer powers of log. That is a restriction that we impose because it's related to Dulac's problem. So for us, the powers of the logarithms have to be integers, possibly negative, but integers. Of course, the power alpha here have to be bigger than 1. The coefficients are real as usual. the number n alpha is an integer, which could be negative. And of course, we impose the usual condition of well-ordering of the exponents. Am I clear? So this is the kind of logarithmic transseries we first considered. So what do we want to do? We want to linearize, if we can, or to normalize, if we cannot linearize, such a transseries. That is, after a conjugation by an element of the same class L1, we expect a simple normal form. So how do we proceed to do that? So let's rewrite f as I do here, x plus a first monomial, a x alpha L1 to the m, plus monomials of higher orders. And we want to find a simple normal form. That is, we want to find an element f hat of the same class of transseries, such that the conjugate f composed with phi composed with f composed with phi minus 1 kills as much as possible terms of f. This is how we expect to find a normal form. So the problem is how to find such a phi. That is, how to find the conjugation here. Well, we do that by expressing phi as a transfinite composition of what we call an elementary transformation. So the question is, what is an elementary transformation? An elementary transformation is simply that. It's x plus a single term. The word elementary is quite clear here. So as we want to kill as much as possible terms of the series f, we have to analyze what is the effect of the conjugation of f by such an elementary term. So this is quite a simple computation. And then we are going to iterate similar conjugations in order to destroy as much as possible terms of f, one after the other. Okay, so the effect of the conjugation of f by such an elementary term is the following. The result is equal to f itself. So far, I didn't do harm. Then a, so a, remember that a is the coefficient of the first non-trivial monomial of f multiplied by c, which is the coefficient of the single monomial of the elementary transformation, multiplied by the leading term of an expression which is the sum of two monomials, of two terms, namely this one and this one, plus higher order terms. So this is the effect of conjugating f by an elementary transformation. Am I clear? So you modify f by adding the leading term of this sum, which may depend. For example, one of these terms may be 0 or not. So we have to see. And then we add higher order terms. So what do we want to do? Remember that we want to kill as much as possible terms of f by this process. So let's do so. So in order to kill a term d x gamma L1 to the L in f, so we have to solve the homological equation, namely LT of the sum of the two monomials equals to the term, the opposite of the terms we want to destroy. There is a little typo here before the expression leading term in the last line. I forgot A times C. So it is classically called an homological equation for some mysterious reason that I never totally understood. Okay, so what are the unknown of this equation? The unknown are the data of the elementary transformation. I want to find C, beta, and M such that I can kill by this conjugation here a given term of f. If I can do that for all the terms of f by a transfinite composition of the elementary transformation, if it converges in some sense, then we will have built the normalization of f we expect. Okay, so let's see graphically the effect of this, the resolution of this homological equation. So here you have the support of one element F. For some reason that I do not understand myself, so you have on the horizontal line the alphas, that is the power of X, and on the vertical axis you have the powers of L1. Okay. I don't know why I didn't put any terms on the upper part of the picture, probably by laziness, I would say that, knowing myself a little bit. Okay, so you have in this picture, so you have 1, 0, which corresponds to X, because F is parabolic, so it starts with X. Then you have the first term here, alpha M, which is the bad guys of the story. And you have all the other terms, and you want to destroy all the other terms. Okay, so you start by the first innocent one, which is alpha 2 M2. That is the one. Too bad for him. He is the closer to the bad guy. Okay, so I tend to call the bad guy the sniper. So how does he snipe? Well, he shoots to the first guy by solving the homological equation. So he solved the homological equation, praying his God that this equation has a solution. And what is the effect of the first elementary conjugation? It is that. So as you can see here, the target has been destroyed. So mission accomplished. But at the same time, many other terms which were not here initially appeared. Why? Remember that we had in the homological equation higher order terms. Here they are, the red ones. I forgot them. Yeah. Okay, so at that time of the process, the sniper realized that how can I call that? The sniping party is going to be longer than expected, because each time he kills one guy, infinitely many new guys appear. Okay, but he has to be methodic. So now he's going to kill the next one, and again and again. And the good thing is that when he kills a guy, this guy never reappears in the process afterwards, because we are adding higher order terms each time. So this guy never reappears, probably because he shoots in the head. And this is my little tribute to zombie movie. Okay, so we are going to kill slowly but surely all of them except the gray one here. Do you see the gray one? No, you cannot see the gray one. What did I do? What did I do? Ah, where is the gray one? The gray one is here, because there is exactly one pair of exponent alpha m for which the homological solution equation doesn't have solution. So this one is going to survive to the entire process. So the details of the proof consist in proving that composing all these elementary transformations converges in some sense. This is what we did. So the result now is the following. Isn't it fun? It is fun, right? If you start from a parabolic transserial series, purely logarithmic series here, well, it admits by a convenient conjugation by also a parabolic series tangent to identity, it admits the following normal form: X plus the sniper. The sniper never dies in the story. That's quite moral. The bad guy never dies. And the gray guy, which is invisible because it cannot be solved. You cannot solve the homological equation for it. So this is the best formal normal form you can expect for parabolic transseries in L1. So let me add another comment here. So if you remember what I said at the beginning, in this kind of problem, everything is a matter of the size of the group. Here, of the group of conjugation. Here, I don't want a too big group of conjugation, because otherwise the classification would be too coarse. So in particular here, you see that the conjugating map is in the same class L1. We do not need iterated logarithm. But there is a funny thing here. If you allow yourself a double iteration of logarithm, you can simplify this normal form in the following way. The normal form will be simply, I'm too fast here, f tilde 0 downstairs, which is x plus the sniper. So if you allow a conjugation by a bigger group of conjugations, then you can simplify. And this is the ultimate simplification you can expect in this class, further the initial parabolic series. Okay, so as I said, it's a matter of balance, depends on what you want to achieve at the end. So our obsession is in general not to go too far from the initial set in which our initial series live. Okay, little example of this process. Start with f hat, which is lambda x minus xl1 plus higher order term. The normal form here is lambda x minus xl1. So you cannot have better. Okay. Now skip to another class. After this fantastic success, we wanted to go further, that is to consider logarithmic Chern series with iteration of logs. And the question is, can one expect similar results? Well, so let's analyze that a little bit. So this was done by, okay, creation names, Peran, Resman, service half creation, let's say, for today. And we studied what does mean LK? LK means basically logarithmic Chern series in which we allow k level of iterations of the logarithms. Hyperbolic means that such a sum series starts with lambda x, where lambda, the multiplier, is not 0 nor 1. So we had a result for hyperbolic Chern series. Dino Peran alone had a lot of results, quite a beautiful work for all the class written here, parabolic Chern series, strongly hyperbolic Chern series, always for only logarithmic Chern series with iteration of logarithms, but no exponential. Okay, again, I introduced the same variable L1, and now I introduce the iteration of L1, so the LK, which all are infinitesimal variables, and we have the monomials, which are products of the variable x with positive real exponents and integer powers of the logarithms. And you can order these monomials in the following way. X is smaller than L1, smaller than L2. It's not like the classical situation at infinity, but it is reversed here. So L1, so minus 1 over log x, is infinitely bigger than x, typically. Okay, so consider a series in this class. So the way that we write this series is a bit different than before. Now we consider them as, how can I say, organized by the powers of x. That is, every series can be seen as a sum of a power of x, x alpha, multiplied by a block R alpha, which contains only the variables L1, L2, L3, Lk. So more precisely, R alpha can be written as on the board. Okay, so we have a theorem. So let me state precisely at least one theorem here, and you will see how unpleasant it is. Sorry about that. Okay, let's assume that lambda is, as it is the case for hyperbolic situation, between 0 and 1. The normal form of f, which is equal to lambda x plus, are you ready? No. X multiplied by, so what is it? It is, so x is multiplied by a sum of monomials in log, where the exponents of the logarithm are integers, which are between 0 and 1. And when I say 1, I mean 1, 1, 1, 1, 1, because m is a tuple here. plus higher order terms. So M is a tuple. So when I write 1, yeah.
Each component is bounded by 1?
Yeah. Yeah. No. I mean that M is lexicographically smaller than 11111. Okay. Then in that case, after a conjugation by an element of the same class LK, we have the following normal form. Lambda x plus precisely those monomials that I have written here. So let me try to explain a little better here. We are close to 0, though. So the bigger the exponents, the smaller the monomials, right? X10 is smaller than x. So here, what we keep in the normal form is simply the sum of all the monomials which are bigger than the precise monomial x times L1 times L2 times Lk. So we keep all these ones, and this is the normal form. So you see that if you compare to the initial results in the hyperbolic situation, which was a linearization result, we are far from it here. So we are far from being, the linearization result would mean that the normal form is lambda x. Well, it is not the case. Well, it's a bit unpleasant, but as Robert De Niro says to Al Pacino in the Scorsese movie, The Irishman, it is what it is. Okay, so we have this. So I'm not going to show you the entire proof of this result, but there is one point of the proof which I find funny. I have a special sense of humor, I agree, which is the following. Before the proof, let me give you an example of what this normal form could look like. Consider the series f, which is lambda x, hyperbolic, plus x multiplied by, can you read, sum of L2 to the k, plus L1, L2, plus L1 square, plus higher order terms, which are sum of xk. So here, in this series, if you follow, you can detect the normal form by yourself. I keep all the monomials which are bigger than the monomials x times L1 times L2. So what is left? The normal form is F0, which is lambda x plus x multiplied by the sum of L2 to the k multiplied by L1, L2. Meaning that the normal form not only is not linear, but it also has a support of infinite cardinality. The normal form is not finite, if I can say so. Well, again, it is what it is. Okay, an ingredient of the proof. Consider, so I'm working here in the class L2. L2 means that we have only 2 iterations of the logs, L1 and L2. I am introducing a class of purely logarithmic monomial in the story. At some point, we had to solve a differential equation. So I'd like to show you how we solve this differential equation. I cannot explain without going into too much details how this differential equation appeared, but let me show you how we solved it. So let me write this differential equation. So consider 3 elements of this purely logarithmic series, such that you can forget the details, such that the monomials are small enough, meaning that the exponents are big enough. And consider the following differential equation. So L1 squared di over dL1, so we derivate with respect to the variable L1, plus R1 multiplied by y, plus R2 multiplied by the sum of hk, yk. So this is a nonlinear part of the equation, where each hk, again, is purely logarithmic and with a monomial big enough, equal to a right-hand side, which is R. So typically, this is the kind of differential equation we'd like to solve. So as you can see, it's a first-order differential equation, nonlinear, because of this infinite sum here. So how did we proceed to solve that? Well, we introduced on this set of purely logarithmic transseries a distance, a metric, for which this set would be complete in the sense of a metric space. And then we solved the fixed point problem in order to solve this differential equation. So how did we proceed more concretely? Actually, we equipped a smaller space, but okay, this is detail. So the metric, what is the metric? The metric is the metric adapted to the order with respect to the variable L1 in this space of logarithmic transseries in L1 and L2. So we have here Banach space, and we define not one operator, but two. This is a little trick that we do repeatedly in this paper. Usually we cannot have a single contraction operator, so we use two operators. So what is S and what is T? S consists in considering totally the non-linear part of the differential equation, namely the right-hand side minus all the non-linear parts of the differential equation. And what is T? The T is the rest. So T is the purely linear part of the differential equation. And we observe by some elementary computations that in that case, so obviously the differential equation can be rewritten that way. So instead of a fixed point classical thing, meaning that P of something equal to something, here we have two operators which have to share a common value. So it's a slight variation of the classical fixed point method. So in that case, we observe that for the distance introduced above, S is a 1/4 contraction, T is a 1/2 homothécy on the space. And moreover, we prove that S of B is contained in T of B. That is, the range of S is contained in the range of B. You see what it means? It's in that an element of this range must be the image by T, that is by the linear differential operator here of something. Meaning that we have to prove this inclusion here. We have to prove that for each element of the range of S, we have to solve the linear differential equation given by this first order operator. So that can be achieved by easy formula, the classical formula for solving first order linear differential equation. Everybody here knows how to do that. Okay, so this is basically what is written here. And now remember that we have to solve an equation which is S. Well, let me show you again. This one. I think I have destroyed completely the pointer. It's not for this one, not completely, but this one. Okay, the two operators have to share one same value. So there is a general theorem which states exactly that. I call that a fixed point theorem. So if you consider a complete metric space, X, two operators such that first, S is a mu Lipschitz map. Second, T is a lambda homothécy. Third, mu is strictly smaller than lambda. And finally, the range of S is contained in the range of T. If you assume that, then there exists a unique element of the metric space such that T of X is equal to S of X. So this is exactly this general result, topological metric result that we applied to solve our differential equation. Actually, this is nothing but a fixed point theorem because thanks to the hypothesis, the operator T minus 1 composed with S is a well-defined contraction because mu divided by lambda is smaller than 1. So you apply the classical Banach fixed point theorem. So actually, it's easy. The thing is, it's a trick that we use repeatedly in all our work, which is used when you don't have, you cannot translate your conjugation problem into a fixed point problem immediately. So then you split the operators which appear in your problem into two parts, S and T here. and it is used repeatedly. And here, the more interesting part, I think, is when it is used to solve a differential equation. What time is it? It's over, no? Okay, it's over. It's over. Thank you very much.
Before I open the floor to questions, I would make a comment on the delicate matter of paternity. The sentence, "it is what it is,"
Yeah.
has been coined, it's the signature sentence of Donald Trump well before the Irish.
Oh mon Dieu. Okay. Okay. I regret it so much.
Yes.
It was so funny in the movie, but okay. Okay, I didn't know that.
That being said, more serious questions or comments?
It's impossible. After that, it's impossible. Everybody is terrified. I mean, look at them. They're afraid to quote Putin without knowing it. I mean, you know what? Except, of course, Michael.
Can you know what real powers of log?
Well, we're working on this now. Of course, we're working with Dino, a bit with Vincenzo and Tamara. We are working on this to extend the class of these methods. So we expect to extend our methods at least to real powers of the log, and maybe to more to wider class of transseries instead of I might make mistake here, instead of LE, EL, again without E, if I can say so. So EL without E. I think it's called L. Yeah. And introducing the exponential, by the way, in the story, we have no idea for the moment by our methods. So we have to completely rethink the problem.
Yeah, first you talk about the hyperbolic case where there are no logarithms.
Yeah.
Then you have analytic conjugation.
Yeah, right. Linearization.
Linearization.
Yeah.
Then you talk about hyperbolic logarithmic series.
Yes.
But you didn't talk about the convergence problem.
So it's a good question. In the case of, well, not convergent, but germs with asymptotic transserial expansion. So we have some results in the case of Dulac germs. So the germs which appear in the original Dulac case with a non-degenerate polycycle. Okay, so in that case, the hyperbolic case leads to linearization on the side of germs. So I guess it answers your question. So and again, so our goal is to work on germs more and more. So there are other results in the parabolic situation dealt with by Maya Resman and Paweł Marwezicz. I don't know them by heart now, but you can ask Maya.
In the classical cases, you have this number of forms and they can be embedded in a flow.
Yeah.
True for this.
Yeah. Yeah. For no, not for all of them. For in L1, it's done. That's a good question. Well, there is another work by a mathematician called Edgar, which has been pointed to me by Matthias Aschenbrenner a few years ago, and which has been studied. His work has been studied by Vincent Bagayoko this year. So correct me, Vincent, if I'm wrong. Edgar proved that for so-called transseries with level 0, you can embed them in a flow. The thing is, Edgar uses the entire transseries as a possible group of conjugations, which is kind of opposite of what we want to do here. We try to find our normal form by smaller reasonable group, not the bigger one, okay, biggest one. But if you are only interested in embedding in a flow, that problem can be solved in general. Well, of course, the element of the flow can be complicated because if you allow conjugation by a complicated trans series, you will get complicated element in the flow. But we did it completely in L1 and flow also in L1. Excuse-moi, je suis complètement sourd. No, no, it's okay. Don't move.
In terms of the type lambda x plus xl,
Yeah.
or lambda x plus xl2, or
Yeah.
whatever.
Yes.
You can put. So in the case lambda equal to 1, we call them parabolic, if I'm correct.
Lambda x plus,
Lambda equal to 1,
yeah,
so x plus xl
yes,
equals parabolic.
yeah, right, yes.
So I was wondering about the dynamics of these germs. It's like too small to have any metals.
Yeah.
And
I thought you have solved this problem actually. No, it's not true.
no, it's always alpha bigger than
Okay.
1.
Right. Okay.
Alpha
Okay. Now alpha is smaller than. Okay.
If alpha, so if it's z plus zl.
Yeah. I don't know. I mean, what could we expect? I mean, thin petal. You mean thing like that? I don't know. Yes, it's something we have to consider. I have never considered that so far. Yeah.
Are there any other questions? So I have a reverse question. So I see here that you are in the context of a complete metric space and you're using a fixed point 0.
Yes.
But I mean, in the context of ultrametric spaces, there is a whole series of ultrametric fixed point 0. So the reverse question, is there a context where you could actually imagine using
possibly, yeah, it's a good question. Possibly, this is the kind of other metric or ultrametric that we have to consider in order to extend our results. So I believe, we have not done that yet, but I believe that studying all this ultrametric fixed point statement would be very helpful in continuing this work. Yeah, I'm convinced of that.
Other questions or comments? If not, before thanking the last speaker, I would like to take the opportunity to say that this is the last lecture of the last workshop in this thematic program. And I would like to take the opportunity on behalf of the organizers of this workshop and on behalf of all of us, I hope, to thank very much the organizing committee of this thematic program that has been ongoing since January and is ending on June 30th. Since this is maybe one of the privileged time where we see a lot of people in this room. So I would like to extend our thanks to Gal Beniamini at the Weizmann Institute, Philippe Hieronymi at the University of Bonn, Mikael Matusinski, here present, Tamara Servi, and Patrick Speisiger. And special thanks, we know that some of you here, at least, did I forget someone?
No, don't think so. You have five names.
5 names.
Perfect.
Yeah, 5 names. And we know that some of you have been living through this winter here in isolation. So thank you for holding the house. And special thanks to the very generous support that we got from Gal and from Chris Miller last night into the young people. Thank you so much. And after we thank Jean-Philippe, we will all proceed to the spiral staircase if you like to be included in the last group photo.
May I say something before we? Yeah.
Okay.
Well, I have already a mic. So before you do whatever you want, I'd like to ask you to thank the organizers of this precise workshop. Salma Kuhlman here, Fernando Sanz here, and the shadow organizer that nobody sees, but who is probably watching us like Big Brother Georges Comte from University de Mont Blanc, Savoie. So many thanks for this organization. It was very nice, and maybe another time.
I would like to take this occasion also to thank all of you as participants, of course, for having taken the risk to come here, even with this pandemic, with this problem, it has been complicated. We'd like to give a special thanks to our great lecturers, courses we had that were so rich, so diverse. We can all thank them. And well, of course, as you said, the organizers of the workshop, the first workshop too, even if it were online, it was tricky. We did it. We had a great program, and thanks to you all.
But the program is not finished, so if you hang around till June 30th, you still have to work.
Excellent, excellent.
Don't think that it's vacation time.